So good afternoon everyone. So as a part of this PMRF session. So in this session we will talk about some. So the title of the course is Advanced Chemical Thermodynamics and Kinetics. So this is a tutorial session. This is sixth session. So another sixth session is there. So your exam is also there. So be careful in handling whatever I have taught you since five sessions. These are enough materials, and you can look some books also. If you want any help regarding books, please let me know. Okay. So in today's session, we will start now. So first is today's session will be basically on the partition function. So if you look at a system of molecule, if there it has a different energy and different energy state. So sometimes at different temperature, this particular system maybe they of different population, and based of the population, you can get the how much is the population fraction is different energy state. So that is the reason that is the basic fundamental understanding to take partition function as a consider. If you take a partition function, and with the help of the partition function of the system, you can measure most of the absolute physical quantity like energy. You can measure sometimes entropy as well. But in normal chemical thermodynamics, we have talked about the change in enthalpy, or change in what I will say, change in energy, change in gives energy, change in like enthalpy. But here you can measure absolute value of the parameter. So that is called the contribution from static thermodynamics. So partition function is one of one of the best variable that can be choose based on the upon a system, and based on the energy of individual excited electronic state, we can get the idea about the system. So if you see the first question is this. So I have done answer also. So what is the temperature of a two level system of energy shape 300 centimeter inverse when the population just one half of that of the lowest, right? So if you see that ni equal to n into d minus beta ei, so beta is a constant that is considered as kbt 1 by kbt, and q is the partition function, right? So q partition function can be written as a summation of e to the power minus be epsilon j, so which is taking the exponential form term of all the state, not only ith state. So it is taking all the state, right? Now if you divide n2 by n1, that's see. So the upper state is one half just, then that of the lower state. Here lower state is considered n1, and the upper state population is n2, right? So e to the power minus beta epsilon 2 by beta to the power minus, so this is the value, and delta e by kbt, right? So beta value is kbt, that can 1 by kbt, so that can be proved in statistical thermodynamics as well. So uh, from there, that this delta is the energy difference, that is 300 centimeter inverse, right? Now this n2 by n1, that see it is written that the population of the upper state is just one half, 1 by half by 1 n1, so overall half 1 by 2, so that is 0.5. So this is the value of n2 by n1. And you know about that this delta E epsilon, that can be converted to in terms of joule. So this is the value for converting to get the value of K, right? So this is the value for K for centimeter Kelvin inverse. So this is K. So now in delta is centimeter. So you need to consider about to make this to get the value of K in terms of centimeter in terms of reciprocal of this distance. So that is a centimeter inverse. So here K is coming 0.69506 centimeter inverse into K inverse, where N2 by N1 is going to be uh, the minus delta epsilon by kBt. So from there you can get the value of temperature, and what temperature is basically, this is the formula for this temperature. And you can take so from this equation, if you take log ln from n2 by n1, then ln e to the power minus epsilon by kBt is basically this value. So from there you can get that T value is nothing but T value is going to be a minus epsilon by k ln n2 by n1. So this ln to n2 by n1, that already you know, minus, so negative will be positive, right? So this is the value. So this is 300 centimeter inverse. Now you know the value of K we have already obtained from here, and you will get the value for this 620K value. Please let me know if you have any question. So this is the answer of the first question, that is coming around to 622.7 Kelvin. So that is coming around 623 Kelvin. So this is the value second questions. This is the answer of the second first question, 623 Kelvin. if you see
the first one now, if what will happen if you the first question, so we will come to the second question where we will talk about
about the another we'll take the another
comparison coefficient.
now going to the next questions, where need to calculate the transition partition function of an iodine molecule at 300 Kelvin. Assume volume to be 1 liter. Okay, so you need to calculate the transition partition function here. Venkat, hello, hello, hello. No, 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 I am not going. I came around 2. Okay, I am taking from my room only. Hello. Okay. Yeah. Yeah. Sure. Sure. So now, if you see in case of here, uh, whether I was audible or not, I don't know. So if you see the here, so you know the mass, that mass of iodine is 2 into 127.
127 is the
Molecular weight for iodine, for only iodine atom. So just a minute. Yeah, so now you have to calculate the mass of only one iodine molecule. Okay, so one more, so that's why we are in 2 into this. So this is for 2 into 127, so this is the mass for 1 mole of iodine, right? You need to calculate only one molecule. Okay, molecular mass. Okay, so that's why mass of iodine is into 127 into 1.6606 into 10 to the power minus 27. Okay, so now this is the mass of iodine. Now you know this formula 2 pi m kBT, so that is required for for translational partition function. So this is lambda is the translational partition function, so that is equal to h by root over 2 pi m kBT, root over 2 pi m kBT. So this h is the value for the 6.626 to into 10 to the minus 34 joule into second, and 2 pi m kBT. So this is the basically giving the this is giving the value around 1.0969 10 to the minus 44. As a result of which, if you take a square root of this, so you are getting this partition function, structural partition function around 6.326 into 10 to the minus 12 meter.
So
This is the wavelength, right? So meter, and the transfer is volume by that cube. So this is a unitless quantity. Remember, always partition function is unitless quantity for transfer partition function. So this is the answer for the second question. Like 3.95 into 10 to the power 30. So this is the answer for second question. Please let me know if you have any query. So this is the where you can get the value of this this transfer partition function, which is coming around 3.95 into 10 to the power 30. This is the translational partition function. Now we'll go for the third questions. In the third questions, So in the third question you need to calculate the vibrational frequency. So we calculated previously, the first one is the temperature required for this like two level energy system based on the fraction of populations. Here we calculate about translation, now we will calculate about the vibrational frequency. So the can you so the vibrational frequency of a homonuclear diatomic molecule is this mu, okay. Yeah. The temperature at which the population of the first excited state will be half that of the ground state. So this so there are multiple options is there. So this is the equation from ith level population for this frequency. So in I equal to gi into e to the power minus ei, basically as same. So beta epsilon I beta equal to 1 by kBt. So just half the kind of same kind of things. Then now it is a vibration, so energy will be mu plus half, right? So now E1 and E2, just first excited state ground state is 0 and first excited state is 1, that of the ground state, so and 0. So this eta 1 eta 2 eta no, and eta 2 is half, into is half by 1, so half, right? So same, so basically 1 and 3 they are basically same kind of problem to be approached. So just think about it little bit. now this eta n2 by n1, so this is basically like 1, so this n2 by n1 is half, so e to the power minus half h nu by kVt, so overall you are getting 2 into e to the power this value. So from there you can get the temperature, so h nu into log 2 into kVt, right? So h nu by log 2 into kV, so D is the answer here, right? So answer is D. Now you go to the another questions. The other question is on this: calculate the characteristic rotational temperature and rotational partition function for hydrogen gas at 2727 degrees Celsius, given that the moment of inertia of hydrogen gas molecule at this temperature is 4.6033 into 10 to the minus 48 kg per meter square, kg into meter square. So here you need to calculate characteristic rotational temperature, right? So in this question, just a minute. So you know that this this rotational partition was equal to a square by 8 pi square I into k. K is r by na value. So this is the value of k 1.32 minus 23, and this is the Planck constant where and for hydrogen sigma equal to 2, and this is the Planck constant where this h value is 6.62 into minus 34 whole square by 8 pi square 3.14 to I moment of inertia. So moment of inertia is giving already, so this is the mass and the distance square, so 4.6033 into 10 to the minus 48. So overall the value is coming this 87.49 Kelvin. So you know that rotational partition function equal to T by sigma into Q rotation, right? So characteristic rotation, this temperature value, this rotational temperature Q rotation, capital Q rotation, this is small q rotation equal to T by sigma into Q rotation. So 3000 is the temperature. They have already means just you plus 273 if you add, so this will degree Celsius converted to Kelvin. As a result, this 3000 is coming by 2 is the sigma value, 2 into 87.49 Kelvin. So this Kelvin will be cancelled out. So overall you are getting 17.144. So this is the value for this. So your value is 87.49 and 717.14. So D is the answer here. This there is a symmetry value, the sigma is 2 for homodiatomic molecule. So two rotational axes can be possible. So this is the rotational quantum number. Now came to this question. I need to find the molecular partition function for a system in which energy levels are equispaced by energy by E is equispaced energy level is vibrational partition function. So Q vibrational equal to 1 by 1 minus e to the power minus h nu by kBt. So 1 by 1 minus e to the power minus e into e by kBt. So this 1 by kBt is considered as beta. So that's why it is considered as Q vibrational 1 by 1 minus e to the power minus epsilon into beta. 1 by 1 by e to the power minus epsilon into beta. So answer is B. Now come to this question, the probability of finding the harmonic oscillator energy level n equal to 1, right? So this probability is written as e to the power minus e by kBt by q, e to the power minus e by kBt by q. So overall this vibrational partition function is coming 1 by e to the power minus h mu by kBt. So e to the power minus 1 because h nu equal to kBt. So this is the probability of finding the harmonic oscillator e to the power minus 1 by 1 by e to the power minus e to the power minus 1. So e to the power minus 1 into 1 minus e to the power minus 1. So overall it is coming e to the power minus 2 into e to the power minus 1, e to the power minus 2 into e to the power minus 1. So your answer will be D. If you see for the next session where we will talk about the another question. So consider a two-state system at a thermal equilibrium having energy. This is very important. Having energy 0 and 2 kBt, for which the degeneracies are 1 and 2 respectively. So what will be the value of partition function at the absolute temperature? So if degeneracy comes into play, so this is summation of g into e to the power minus epsilon I by kbt, right? So g1 into e to the power minus 1 by kbt plus g2 into e to the power minus 2 by kbt. So overall g is written as 1 into e to the minus e to the minus 0 by kbt plus 2 into e to the power minus 2 kbt by 2 kbt. So 1 plus 2 into e to the power minus 2. So overall it is coming around 2 into, so this e value, if you consider e to the power minus 2, so it is coming around 0.1353 equal to 1 plus 0.2706. So overall it is coming around 1.27. So this is answer is A. So this, if degeneracy comes into picture, then you have to take the degeneracy of each individual energy states. So each energy state may have the same may be non-degenerate, but each of the energy state may have different degeneracy, right? So degeneracy means, what is the definition of degeneracy? So number of accessible quantum state in a particular energy levels, right? So that is called a degeneracy. If it is a non-degeneracy means only one, right? If it is a three means three, like this. So here the degeneracy already they have told 1 and 2, right? So this A is the answer here. So you understand. So first we have this first question where we need to calculate the uh, temperature at which that population of the second population of the upper state will be just half of the lower state. Oh my.
This was a problem with the solution.
Okay, so here in this question we have the vibrational frequency is given. So from there you don't need to calculate the temperature at which the population of the first excited state is basically the half of the ground state. So as you can see, most of the question they are asking for the temperature as well as the condition for this ground first excited state populations. This is the forum where you need to find the rotational temperature as well as rotational partition function. This is a question where you need to find the molecular partition function, and this is a question finding of probability for the finding of a harmonic oscillator. Now here, so they have given the degeneracy 1 and 2 respectively, and what will be the partition function at the absolute temperature. So we'll go to this question. Yeah, so this question is a little bit important. So before that, just you look at the questions, what can be the possible, like how it will be approachable. here you need to find out the temperature, right? So how these questions can be approachable, one need to see. Now if you look this question, so here energy equal to nh nu, that everyone knows. So is zero, you know this zero vibrational level, like vibrational partition function related to zeroth level. So each energy level has a different energy, as a result of which you will have a different partition function, right? So overall all summation of all the partition function will be 1. There is translation, rotation, vibration, everything. So Q vibration equal to 1 by 1 minus e to the minus theta by t. So for high temperature is extremely high, right? So theta by t is very less, right? E to the minus theta is 1 minus theta by 2. You know that e to the minus x series, e to the minus x can be written as e to the minus x square by 2 factorial, something like this, right? So like this way, 1 by 2 factorial into this value, right? Now this can e to the minus x can be written as 1 minus x, right? So same way, e to the minus theta by t, 1 minus theta t, right? So cube vibration equal to 1 by 1 minus 1 minus theta t. So this is basically 1 by theta t by theta, right? T by theta. So your answer will be B, right? Just look at this calculations, how it can be done. So here the q vibration will be theta, will be t by theta. Now we will go to the next questions, where we will, just a minute, where we will show that the single partial transitional partitions for that v by lambda v by lambda cube, right? So that is the wavelength, basically the, which is the value is q by 2 pi m kbt whole to the power 3 by t, right? Just if you do this, so lambda, so q equal to v, so v by lambda cube, right? So the single particle transition partition function f of an ideal gas in fixed volume v depends on thermal de Broglie wavelength lambda. So lambda, what is the value of n, right? So n value is simple, so you know that q transition is v by lambda cube, right? That's all. So v into lambda to the minus 3, so is proportional to lambda into the power to minus 3, so n value is coming in minus 3. Now comes, so what is the symmetry of this O3? So this is sigma 2 symmetry, right? O3, right? So this was the first question, whatever we have. Just look at the questions little bit. So now if you see this one, so in most of the case you need to find out this value, right? So where is my, yeah, this is my, so here you need to find out the temperature, where in the next case you need to find out the value of transition partition function qtr, and here you need to find the value of this temperature. So they are basically allowed to like these questions are talking about this temperature calculation as well as this partition function coefficient, partition function what I'll say, this partition function transitional rotation vibration, something like in all the cases, and the symmetry number, right?